This is Beyond the Business.
In June 2023, something unusual happened in North America. Massive wildfires were burning across Canada. Smoke from those fires traveled thousands of kilometers south. Within hours, the skyline of New York City disappeared behind a thick orange haze. Air quality monitors recorded levels above 400 on the Air Quality Index, placing the city among the most polluted places on Earth for several days. At one point, the air quality index in New York reached levels normally associated with some of the most polluted megacities in the world. People wore masks in the streets, flights were delayed, schools cancelled outdoor activities. For many residents, it was the first time they experienced what extreme atmospheric pollution actually feels like. Yet the fires themselves were thousands of kilometers away. This moment revealed something important. The atmosphere does not recognize borders, and it does not change according to policy timelines. While governments build regulations around specific pollutants, the atmosphere evolves continuously. By the time one environmental problem is understood and addressed, another may already be forming. These are the moments when atmospheric policy begins to lag behind atmospheric reality. One of the clearest examples appeared in the late 20th century. During the 1970s, scientists began noticing something alarming. The protective ozone layer in the upper atmosphere was thinning. Ozone is composed of three oxygen atoms. High in the stratosphere, it absorbs harmful ultraviolet radiation from the sun. Without it, life on Earth would face far greater risks of skin cancer, crop damage, and ecosystems collapse. Researchers eventually identified the cause, a family of industrial chemicals known as chlorofluorocarbons or CFCs. These compounds were widely used in refrigerators, air conditioners, industrial solvents, and aerosol spray cans. They were chemically stable and safe to use at ground level. But that stability allowed them to drift into the upper atmosphere. There, ultraviolet radiation broke them apart, releasing chlorine atoms. A single chlorine atom could destroy tens of thousands of ozone molecules. In the early 1980s, scientists discovered a massive seasonal ozone depletion above Antarctica. The phenomenon became known as the ozone hole. The global response was unprecedented. In 1987, governments signed the Montreal Protocol. The agreement phased out most ozone-destroying chemicals. It remains one of the most successful environmental treaties ever implemented. Today, the ozone layer is slowly recovering. But solving this crisis introduced another challenge. Many replacement chemicals used in refrigeration and air conditioning were hydrofluorocarbons or HFCs. They don't destroy ozone, but some of them are thousands of times more powerful than the CO2 as greenhouse gases. In solving one atmospheric problem, the world unintentionally created another. Today, global climate policy revolves around a single number: carbon dioxide. Before the Industrial Revolution, atmospheric CO2 levels were about 280 parts per million. Today, they exceed 420 parts per million. This increase is largely driven by fossil fuel combustion and industrial activity. As a result, most international climate frameworks focus heavily on carbon dioxide emissions. Carbon markets, emissions trading systems, corporate climate targets all revolve around the same metric: CO2. Today, carbon pricing systems influence roughly a quarter of global greenhouse gas emissions and represent tens of billions of dollars in annual trading across international carbon markets. But the atmosphere is not governed by a single gas. Methane, for example, has a warming potential roughly 80 times stronger than CO2 over 20 years. Nitrous oxide has a warming potential nearly 300 times stronger than carbon dioxide. Black carbon particles influence ice melting in polar regions. Water vapor amplifies warming through feedback loops. Yet global climate governance still relies heavily on CO2 equivalent calculations. This simplifies policy design, but it can also obscure the complexity of the atmosphere itself. The atmosphere is not a single variable, it is a chemical system involving hundreds of interacting compounds. Another atmospheric blind spot involves aerosols. Aerosols are tiny particles suspended in the air. They come from sources such as coal power plants, diesel engines, industrial emissions, forest fires, and dust storms. From a public health perspective, aerosols are extremely dangerous. Fine particles known as PM2.5 can penetrate deep into the lungs and bloodstream. According to the World Health Organization, air pollution contributes to roughly 7 million premature deaths every year. Reducing particulate pollution is therefore a major public health priority. But aerosols have a complex climatic role. Many aerosols particles reflect sunlight back into space. This creates a temporary cooling effect in the atmosphere. Some climate scientists estimate that aerosol pollution has masked up to 0.4 degrees Celsius of global warming. In the late 20th century, the rapid reduction of sulfur emissions in Europe and North America significantly improved air quality but also reduced part of this cooling effect. In other words, some industrial pollution had been partially offsetting the warming effect of greenhouse gases. Cleaning the air improves public health, but it may also reveal warming that was previously hidden by aerosol pollution. The atmosphere does not respond to individual pollutants in isolation. It reacts to the balance of many substances simultaneously. While global climate policy focuses on carbon emissions, several emerging atmospheric influences are beginning to attract scientific attention. One example comes from aviation. High altitude aircraft produce condensation trails known as contrails. These artificial clouds trap heat in the atmosphere. Recent studies suggest that contrails may contribute as much warming as aviation CO2 emissions themselves. Another emerging concern involves ultrafine particles, sometimes called UFPs. These particles are far smaller than PM2.5. They are increasingly produced by modern combustion engines and aircraft turbines. Because of their extremely small size, they may penetrate deep into the human tissue and potentially affect cardiovascular and neurological systems. Yet, regulatory frameworks for ultrafine particles remain limited. Another surprising discovery involves microplastics in the air. Recent studies have found microscopic plastic particles circulating in the atmosphere and traveling thousands of kilometers through global wind systems. These particles have been detected in the remote mountain ranges and polar regions. Scientists are only beginning to understand their long term environmental and health effects. Recent estimates suggest that thousands of tons of microplastic particles may circulate through the atmosphere every year. Each of these examples illustrates how new atmospheric influences often emerge before regulatory systems fully recognize them. One of the largest atmospheric risks may lie in the Arctic. Across northern regions of Siberia, Canada, and Alaska, vast areas of land are covered by permafrost. Permafrost is a permanently frozen soil, but it contains enormous quantities of organic material trapped for thousands of years. Scientists estimate that Arctic permafrost stores roughly 1,500 gigatons of carbon. That is nearly twice as much carbon as currently exists in the atmosphere. As global temperatures rise, permafrost begins to thaw. When frozen organic material decomposes, it releases carbon dioxide and methane. Both are greenhouse gases. Methane, in particular, can accelerate warming rapidly. This creates a feedback loop. Warming melts permafrost, permafrost releases greenhouse gases, those gases cause further warming. If even a fraction of this carbon is released into the atmosphere, it could significantly accelerate global warming. Yet, permafrost emissions are extremely difficult to regulate. They are not produced by factories, vehicles, or power plants. They are produced by the Earth system itself. In other words, one of the largest future climate risks may come from natural systems reacting to warming than humans have already triggered. These examples reveal something fundamental about atmospheric policy. The atmosphere is not static, it is constantly evolving. New technologies change emission patterns, new chemicals enter industrial production, new natural feedback systems emerge. Environmental policy, however, moves more slowly. It requires scientific evidence, international negotiation, and regulatory implementation. This creates a structural gap. The atmosphere changes continuously. Policy frameworks respond step by step. As a result, humanity often finds itself solving yesterday's atmospheric problem while tomorrow's problem is already forming. None of this means that environmental policy are ineffective. In fact, some have been remarkably successful. The Montreal Protocol reduced ozone-destroying chemicals. Air pollution regulations improved air quality in many cities. Carbon policies are beginning to reshape global energy systems. But these successes also reveal something deeper. Managing the atmosphere is not a problem that can be solved once. It is a process that must constantly adapt. Each technological solution changes the system. Each policy creates new incentives. And each shift in the global economy introduces new atmospheric dynamics. The atmosphere is not just an environmental issue, it is a complex planetary system shaped by chemistry, physics, technology, and economics. Understanding emerging risks may become just as important as solving the problems we already see, because atmospheric systems evolve faster than most regulatory frameworks. And by the time one problem is solved, the next one may be already in the air.